This video is going to introduce the concept of ionization energy. Ionization energy is the energy required to remove an electron from an atom or ion in the gas phase. So here we see a hydrogen atom on the left, and you can see that on the left it's a neutral atom with a single proton and a single electron. And the energy required to pull that electron off is 1,312 kilojoules for every mole of hydrogen atom. And you see on the right that you have a hydrogen +1 ion and then the separated electron. So ionization energies, let's start with a set of ionization energies for a given element. And we'll use magnesium as our example, but we could use anything. So we have neutral magnesium atom in the gas phase, and we're going to remove one electron, and that's going to form magnesium +1 cation if we just remove one electron. So the energy required to do this is abbreviated. So the abbreviation for ionization energy is either IE or E with a subscript I. This particular reaction that I've shown here describes what's called the first ionization energy of magnesium. So this would be the energy required to remove that first valence electron, which is going to form magnesium +1 ion because you're only removing the first electron. Magnesium's first ionization energy is 738 kilojoules per mole, and so if we had a mole of gaseous magnesium, then it would require 738 kilojoules to remove all of the electrons from that mole of magnesium atoms. Now if we take that magnesium +1 ion and we remove another electron from it to form magnesium +2 ion, that would be abbreviated E sub I2. You can see it requires more energy. We call this the second ionization energy of magnesium. And you can continue on. There's a third ionization energy of magnesium and a fourth ionization energy of magnesium. So these energies would, one thing you should notice is that the energy increases. And so the first ionization energy is always lower than the second, which is always lower than the third for a given element. And the reason for that, I think would make sense if you think about it. For the first reaction, we're removing an electron from a neutral atom. But as we go down, we're forming, instead of removing it from a neutral atom, we're removing it from an ion. And so the ion is getting progressively higher in positive charge. And so it's more and more difficult to remove an electron from a larger positive charge. And we're going to talk about other trends next. We're going to talk about trends between different elements. If we look at the periodic table, we're going to look at trends in first ionization energies next. What you see plotted here are the first ionization energies plotted along Y for all of the elements from hydrogen to calcium. So those are atomic numbers plotted along X, but just think about these as, hydrogen going to helium, you're going across the first row of the periodic table, and then you go to atomic number 3, that's lithium, and you can see the ionization energy falls back down really low, and then it progressively gets larger as we go across the next period. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, that's the second period. And then it drops back down to sodium, and then it goes up across that third period. So we're going to look at these trends. So these are the first ionization energies plotted. So this would be the energy required to remove a single valence electron from each of these atoms in the gas phase. Okay. So if we start by looking from hydrogen to helium, the amount of energy required definitely increases as we go across that first period. So it's much more difficult to remove that electron from helium than it is to remove it from hydrogen. And then here, this is the second period. As we go across this second row, the ionization energy generally goes up as we go across that row. And then here's the third period. Ionization energy again goes up as we go across that period. So this first one is period 1, this second one I circled is period 2, and this third one I circled is period 3. So that's one trend, that ionization energy increases as we go across a row. And so a higher ionization energy means it's more difficult to remove the electron. It gets progressively more difficult. So in a given period, the ionization energy increases as you go across, implying that it gets harder and harder to remove that valence electron. So when we look at columns, if we go from helium to neon to argon, these are the noble gases, and you can kind of generally see that ionization energy decreases as you go down a family. And that's going to be true regardless of which family we use. Here are the halogens. So ionization energy decreases as you go down a column. So let's think about the trends that we see. If we look at period 1, ionization energy increases as we go across this period, and then we can move on to period 2. So let's use period 2 as an example. So as we go across period 2, you go from lithium to beryllium to boron. You're going from a atomic number of 3 to 4, 5, 6, 7, 8, 9, 10 for neon. So as you go across that period, the trend here is the same idea as atomic radius or size. So as you go across, what's happening is your atomic number or charge in the nucleus is increasing. So lithium has a +3 nucleus all the way up to neon has a +10 nucleus. And so the nuclear charge is going up, but the shell number stays the same, which means that it's effectively the same distance from the nucleus, which means that neon's valence electron that you're trying to remove feels a +10 nucleus, which means it has a higher effective nuclear charge because the nuclear charge is higher. So it's going to be much more difficult to remove that valence electron from neon because it has a much higher hold from the nucleus holds it more tightly because it has a higher charge. It's also difficult to remove that last valence electron from neon because neon has a noble gas configuration, which is unusually stable. Now you can see some other issues with stability here, right? You notice that going from lithium to beryllium, it increases, but then it drops back down when it goes to boron. And you can see it goes from boron and then up to carbon and up to nitrogen, and then it falls back down to oxygen again. So there are a few sort of minor trends inside this period 2 that are somewhat repeated elsewhere. You can see there's the same dip from magnesium to aluminum and the same dip from phosphorus to sulfur that we see. And the reasoning there is because if you think about, let's look at beryllium. So for beryllium, we would be removing an electron from the 2s orbital. And beryllium itself has a pretty stable filled subshell. So having both electrons in that subshell is pretty stable, and to remove it would be difficult. But boron doesn't have that issue. If you remove the single 2p electron from boron's valence shell, then you leave it with a filled subshell, which is somewhat more stable than a partially filled subshell. And if you move up to nitrogen, nitrogen has some unusual stability as well. When we talked about electron configurations and orbital diagrams, we said that nitrogen has a helium followed by 2s2, 2p3 electron configuration. And that 2p3, that's a half-filled subshell. So that has some stability associated with it as well. So it's a little more difficult than you might expect to remove that valence electron because it takes it away from that stable half-filled subshell. But oxygen is not as difficult, so it has a lower ionization energy because that would take it to a half-filled subshell like nitrogen has. So you can see some minor trends inside these major trends. Now if we think about the trend of we looked at it going across a period. So it gets more and more difficult because the effective nuclear charge goes up. But why would it get easier as we go down the periodic table here? So lithium is one of the highest alkali metals here, and it has an ionization energy of 520 kilojoules per mole. And then we go down to sodium, which is 496, which is a little bit lower, and then potassium is a little lower at 419. So the ionization energy goes down. It's that it's easy to remove the electron. So it's easiest with this 3, lithium, sodium, and potassium, the lowest ionization energy is potassium, which means it's the easiest to have that electron removed, which means that it's going to be the most reactive when you try to react it with oxygen or hot water or something like that. So these pictures show reactions with water, and you can see lithium just bubbles and it gets hot, and it's more reactive than a lot of other things, but it's far less reactive when you compare it to sodium, which actually catches on fire and burns with that sort of unique sodium yellow flame. And it burns so hot that it actually melts the metal, the sodium. So you've probably seen the reactions of the alkali metals with water. They're pretty vigorous. We probably did it in class. And if you want to watch a video, there's a URL at the bottom here that would show the video. And the potassium is extremely reactive. It actually pops and sparks, and it has that violet flame that represents its emission spectrum. So the activity or reactivity increases as you go from lithium to sodium potassium because that valence electron is easier and easier to remove. And that means its ionization energy is lower and lower. And that's just because it's further from the nucleus. And we're going to do a couple of practice problems to make sure we understand how all of this works in the context of practice. So the first problem here is we're going to put the following in order of increasing ionization energy. We have first ionization energy of magnesium, second ionization energy of magnesium, and the first ionization energies of sodium and rubidium. So if we think about the trends, these first three we can compare to each other because they're all first ionization energies, magnesium, sodium, and rubidium. If we look at where they are in the periodic table, we have magnesium here, sodium is just to its left, and rubidium is down 2 from sodium. So if you remember, sodium and rubidium are both alkali metals. So when we compare those, rubidium should have a lower ionization energy because it is a larger atom, right? It's larger, therefore it has a lower ionization energy because that electron is further from the nucleus. So we can definitely say that rubidium has a lower ionization energy than sodium. Now magnesium and sodium are in the same period. They're both in the third shell. Magnesium is just to the right, and we've learned that ionization energy increases as you move to the right because the effective nuclear charge goes up, but they both have the same shell. They're both in the third shell. That electron removing is the same distance from the nucleus, essentially. It's actually a little closer for magnesium, which makes it difficult because its magnesium is smaller. So ionization energy goes up as we move across, and that means that's because effective nuclear charge goes up, which means magnesium definitely has a higher ionization energy, first ionization energy than sodium, which is higher than rubidium. Now we also have to add in here the second ionization energy of magnesium, which we can't really compare to the other two, but we can compare it to magnesium's first ionization energy. And one of the things we've learned is that the second ionization energy is always larger than the first. They always increase as you go from 1 to 2 to 3 to 4. It gets progressively more difficult to remove electrons from higher charged cations. So this is the final answer here. We're going to move on and do 2A. Consider the trend shown in the graph to the right depicting the ionization energies of carbon. And part A says we're going to write the reaction that corresponds to EI4 of carbon. So this is the fourth ionization energy of carbon. This is the fourth electron that we're trying to remove. Removal of the fourth electron means that we've already removed 3 electrons, which means that carbon is a +3 charge. Now, I understand that some of these things that you're writing look weird. It's very unusual to see carbon as a +3 cation. I understand that. But sometimes you have to suspend your difficulty in writing these things. The reason you don't see it very often is because it's not very stable. So we're not going to easily form carbon with a +3 charge. But we've already removed 3 electrons, and we're going to remove the fourth, which means we're going to form carbon with a +4 charge. Remember that they have to be in the gas phase for ionization energies, and then you also have an electron as a product. All right, now we're going to write the electron configuration of the product of the reaction that you wrote in A. So the product, that means we're going to write the electron configuration for +4 carbon. So if we go, the way we usually do this is we're going to look at our periodic table. Carbon is here, but we've removed 4 electrons, and that's going to be all 4 valence electrons. So if we remove all 4 valence electrons, that means that it's going to have helium's noble gas configuration. 1, 2, 3, 4. So we're going to end with helium. So carbon plus 4 as an ion is just 1s2, right? It's got helium's noble gas configuration, and that's unusually stable. Now, part C asks, why is there such a large increase between EI4 and EI5? And it's related to part B. We formed a really stable cation here. So remember, once we eliminate the valence electrons, we're going into the inner core. So the fifth one would be loss of inner core electrons, which is much more costly energetically. It's much more difficult to remove inner core electrons, not only because noble gas configuration is stable, but because inner core electrons are closer to the nucleus. So all 4 of these are valence electrons, and these 2 at the top are inner core electrons, which is why they are so high in ionization energy.